Welcome to The Explainer. Today, we're jumping straight into a seriously fascinating, high-stakes topic: how we have to actively guide our compilers to unlock massive performance gains on embedded hardware. We often treat our tools like they're infinitely smart, right? But to get the absolute maximum speed and efficiency out of a processor, you really have to become a bit of a hardware whisperer. So let's kick things off by completely shattering the illusion that compilers just perfectly optimize everything automatically. We write the code, hit compile, and boom, we assume the machine code is as fast as it can physically be. But the truth? Well, an unguided compiler can actually introduce massive, hidden inefficiencies. It doesn't know your specific data, it doesn't know your ultimate intentions, so it just has to play it safe.
Here's our roadmap for this explainer. We'll be looking at, first, the compiler's dilemma, then, writing faster loops, 3, navigating memory aliasing, 4, optimizing cache access, and finally, number 5, hardware and custom operations.
All right, section 1, the compiler's dilemma, or why ideal compilers are actually extremely conservative.
To really see this in action, just imagine you're trying to clear n bytes of memory. If you use a standard char pointer, the compiler writes zeros literally one single byte at a time. Why on earth would it do that? Well, because the compiler can't just magically guess if your data pointer is perfectly 4-byte aligned unless we step in and explicitly cast that pointer to an int, basically forcing it to clear 4 bytes at once. The compiler is going to safely, but very slowly, fall back on those 1-byte operations. We have to tell it what's safe to do. And it turns out our software choices constantly clash with the physical architecture. Take loop counters. You might think, hey, I'll use a smaller 16-bit short integer that'll save memory and be super efficient, but on a 32-bit ARM processor. That actually creates a massive penalty. Since the hardware natively only does 32-bit addition, the compiler has to manually generate extra assembly instructions just to emulate that 16-bit wraparound from positive 32,677 to negative 32,768. So you try to be perfectly efficient, but you accidentally force the processor to do a whole bunch of extra work.
This exact dynamic, that constant friction between the software you write and the physical processor architecture it runs on, is heavily detailed in essential resources like the ARM System Developer's Guide. Honestly, deeply knowing your specific hardware is absolutely half the battle here.
Which brings us to Section 2, writing faster loops, and specifically how to count efficiently. Let's see how this builds into the everyday tasks we program.
Even something as totally fundamental as setting a loop counter to 0 gives us some really interesting choices at the hardware level. A standard move operation, like setting I to 0, is fast. It takes just one cycle. But arithmetic operations, like an exclusive OR with itself, or subtracting the variable from itself, also execute in just one cycle. So what's the hidden advantage? Well, those arithmetic operations automatically update the hardware 0 condition flag at the exact same time. That might be exactly what your very next assembly instruction needs to check, which saves you an entire testing cycle right off the bat.
So the really crucial thing to look at is comparing these two approaches to loops, counting up versus counting down. When you count up with an I++, checking if the loop should end means the hardware actually has to subtract your target number n from your counter and then test that result. But counting down? That is a completely different story for the machine.
Counting down to 0 takes exactly one single CPU cycle for the exit condition. No way, right? But it's true. Because as you decrement with I++, the hardware's 0 flag is automatically updated the exact millisecond it hits 0. You don't need any separate comparison operation at all. You just test the flag. It's honestly a beautifully elegant way to shave off cycles in highly repetitive code.
Let's move on to Section 3, navigating memory aliasing, or as we like to call it, guiding the cautious translator.
Think of memory aliasing like two different delivery routes leading to the exact same house. It just causes unexpected traffic and confusion. When you pass multiple array pointers into a function, you absolutely know they represent entirely different sets of data. But the compiler, it has no idea. If it can't guarantee those memory references won't overlap and corrupt each other, it basically panics. It conservatively kills parallel processing, forcing everything to run one by one just to be safe. So it's completely up to us to perform memory alias disambiguation for the compiler.
This is where we step in and act as the hardware whisperer. We can use standard C features like the restrict keyword or no alias pragmas. These act as an explicit, ironclad promise to the compiler. You're basically saying, hey, I guarantee these memory pointers will never, ever overlap.
And once the compiler trusts you on that, it unleashes the processor's full parallel computing capabilities.
All right, on to Section 4, Optimizing Cache Access. The subtitle here says it all, keeping your tools right on your desk.
Because think about it, a cache hit, when the processor actually finds the data it needs right there in its fast local memory, takes maybe 3 to 5 cycles. Quick, right? But a cache miss? That slaps us with an absolutely devastating penalty of 10 to 50 cycles of overhead, because the processor completely stalls out while it waits to fetch data from main memory. If your data isn't structured correctly, your code is literally just sitting around waiting.
You can really see why this matters when we look at multi-dimensional arrays. When the cache pulls data in, it doesn't grab just one single byte, it pulls in an entire block, like a 64-byte line, all at once. In C, arrays are stored so that the rightmost subscript varies fastest. If you accidentally write your loop so the leftmost subscript varies fastest, you're going to cause a brutal cache miss on literally every single memory access. But structure it the correct way, and you're getting 63 fast hits for every one miss. That is an absolute game changer for accelerating your program.
We can use a similar mindset to optimize how our code actually makes decisions. Those massive, bulky switch statements, they completely waste vital CPU time sequentially testing every single case. Sure, you can reorder them to put the most likely cases first, but the ultimate fix is to bypass those huge decision trees entirely. You do this by swapping the switch statement for a lightning-fast table lookup, using an array of function pointers. Suddenly, you've translated a multi-step search into a single, instant jump directly to a memory address.
Now for our final section, number 5, Hardware and Custom Operations. Let's see what it means to truly speak the machine's language. When you're dealing with intensely demanding tasks, like MPEG video processing and the inverse discrete cosine transform, a brute force approach just isn't going to cut it if you want smooth real-time video. To push the processor to its absolute limits, we have to manually layer our optimizations. That means forcing variables to stay inside fast registers, unrolling our loops to eliminate jumping overhead, and introducing some highly complex software pipelining.
And this brilliantly illustrates how software pipelining works in practice. Imagine a loop where one math operation is just stuck waiting on the results of the previous one. That's a true dependency, and it completely stalls the processor. But if you write a 3-stage software pipeline, you literally stagger the operations across the loops. You might be calculating the logarithm for loop iteration number 2 while simultaneously doing the multiplication for iteration number 3. You're effectively hiding those true dependencies inside the loop body, which lets the hardware's parallel execution units run at absolute maximum capacity.
But here is the catch. Even the absolute smartest compiler out there usually can't just look at standard C code and magically map it to the highly complex, custom operations baked into specialized silicon, like a combined multiply and accumulate with shift hardware instruction. So we have to bridge that gap ourselves. We do it by either manually calling vendor-provided assembly libraries or by using specific custom hardware pragmas that bypass normal compilation and directly trigger the silicon. Which leaves us with this final provocative thought. As our embedded systems and processors become ever more intricate, more parallel, and highly specialized, is the perfectly automated compiler just a total myth? Will the software of tomorrow eventually figure all this out on its own, or will we forever need to roll up our sleeves and act as the hardware whisperer? It's definitely something to chew on the next time you hit compile. Thanks so much for joining me on this explainer, and I'll catch you next time.